Hello, my name is Nasny Nevsky, and we're going through Monoidal category theory, the book. And today we're doing chapter 2, which is about categories. We're doing section 2.4, which is a mini course called Basic Linear Algebra. And so it's as follows. We saw a lot of examples of categories, okay, and in a lot of different areas we saw different properties of categories. And now what we want to do is we want to focus on one particular category that we're going to see much of in the coming sections. Okay, and so that one category is called complex vector spaces. Okay, now let me just say so linear algebra studies studies vector spaces, and there's different types of vector spaces. There are real vector spaces, complex vector spaces, rational vector spaces. It doesn't matter. We're going to focus on one of them, namely complex, because that's what we're going to need later on when we talk about quantum computing, quantum mechanics, and lots of other fields, knot invariants and things like that. So complex vector spaces show up very often. So what's linear algebra all about? Linear algebra is all about directions, straight lines, flat planes, cubes of different sizes, or three-dimensional things of different sizes, etc., etc. So they're all about flatness in some sense. Okay, so let me give you. Let's get into it, and let's talk about lots of examples that we're going to have of these things. Okay, so let's just start talking about this category, and let's foreshadow a little. Okay, the objects of this category are going to be complex vector spaces. Okay, there's going to be a lot of them. Okay, so this is the category of all complex vector spaces, and the main thing is how they interact with each other. And so the morphisms are maps between two complex vector spaces, and they're called linear as in straight transformations. Okay, linear transformations. So we're going to spend a third of the time going through this, and then we're going to spend the rest of the time talking about this and how they interact with each other and what that's all about. Okay, let me just two little things. First of all, complex vector spaces show up all over math, all over physics. They're a very important thing. Quantum physics is based on complex vector spaces of a special type, something called Hilbert spaces. Okay, so they show up all over. And second of all is, I don't know how long this video is going to go, but it's nowhere near enough for you to learn what linear algebra is all about. You're going to see a lot of different ideas, but to really understand linear algebra, you have to read a linear algebra textbook. You have to read at least this book and go through a lot of the details. But what I'm going to do is give you an overview of what it's all about and try to whet your appetite to see. It's an absolutely beautiful field, and it has a lot of deep ideas. Okay, so let's dive into it, and let's see what a complex vector space is. Okay, well, we talked about lots of different algebraic structures. In particular, we talked about a group, and then we had things bigger than a group, or with more structure than a group. We had a commutative group. That's a special type of group. We had rings, and we had fields, which have more. So too, this is more than a group. Okay, so this is more than a group. So what's the definition of a complex vector space? Okay, complex vector space, V, is a group, we should say commutative group, okay, abelian group. Commutative and abelian means the same thing. Abelian group. I'll remind you what that is. An abelian group with more structure, okay? So V is an abelian group with more structure. Let's just remember what an abelian group is. There's an addition, there's a subtraction, is a 0 element. So this is the way you combine elements here. This is to give you the negative, and this is when you take x plus minus x is going to give you the 0. Okay, so this is subtraction, and that's called the 0 vectors. So the objects of this thing are called vectors. The objects of V are called vectors. So we have to keep track of what we're doing. We're talking about the category of all complex vector spaces. In particular, each one of them, there's going to be many complex vector spaces. We'll write them as V, V prime, W, W prime, lots of different complex vector spaces. And every single one of them has a set of things in it that it deals with. Those objects within the set are called vectors. Okay, that's just simply convention. Okay, the main operation, of course, is the plus. Okay, but a complex vector space, the complex vector space has another operation, and the other operation is called scalar multiplication. Okay, scalar multiplication, and what that is as follows. We write it as a dot. Okay, it's a function. We write it as a dot. It accepts a complex number and a vector, and this is the vector from here. So it takes pairs of these complex numbers and a vector, and outputs another vector. So for example, we might have 5 plus 3i, that's a complex number, times some vector v, and that goes to comma, so these are a pair, and that goes to 5 plus 3i dot v. Okay, the way to think of it is as follows. Vectors are straight arrows or planes or things like this, and when you multiply it by a c, what you're doing is you're extending it or shortening it. So if this is a v, little v, then you might want to do that, and this is the way to think of it. It's a little bit more complicated when you're talking about complex numbers. That's extending it, but you can also shorten it. Okay, so this is c dot v, and this is c prime dot v for different complex numbers. That's the way to think of it. Okay, now I just want to say you can also talk, and probably if you've ever taken a course by this, you'll probably talk about real vector spaces. And what that is the same thing here, but instead of complex numbers, you do with a real number. And that really fits in better with this intuition of a real number. You can stretch something by a real number or shrink it. If the number's more than 1, you're stretching it. If the number's less than 1, you're shrinking it. That's what we're doing. You could talk about any type of vector space for any field. We're going to not talk about real vector spaces, although you might have seen some of that in linear algebra. We're going to talk about complex vector spaces simply because this is what we're going to need later on. Okay, so it really doesn't make a difference, etc. So we have these two operations that are very important. One is called addition, one is called scalar multiplication. And again, scalar multiplication takes a complex number and a vector and gives you out another vector, which is to be thought of as either shrinking it or enlarging it. Okay, but these operations have to satisfy some rules, some axioms. And so we're going to go through the axioms fairly quickly and show you what they are. Okay, C times, that's a dot, that's scalar multiplication, V plus V prime is equal to C dot V plus C dot V prime. So what that says is the multiplication distributes over the addition. The scalar multiplication distributes over the addition. Next, C plus C prime dot V, okay? Let's say you want to enlarge it or shrink it and you want to add these things. So then you have, this is equal to C dot V plus C prime dot V. So what does that say? That says Well, it says the scalar multiplication distributes again, but over the complex numbers. You're dealing with two things. On this side you have complex numbers. On this side you have vectors. So it's another distributivity rule. Next, C times C prime. Let's say I take C is a complex numbers. Not only can I add complex numbers, I can also multiply them, and I have times V dot V. Well, that's equal to take C prime, dot it with V, and take V, V is a vector. C prime times V is a vector. C times that, do the operation twice, and you get that. Okay, so it's kind of an associativity rule, but again, you have to understand you're dealing with two different things. V is a vector, C and C prime are complex numbers. Okay, one more rule. 1, that's a complex number. It happens to be a very trivial complex number, but it is a complex number, times V is equal to, that's a little v, is equal to little v. In other words, changing it, scalar multiplying it by 1 really doesn't change anything. And the way to think of this is that there's, when you scalar it by a number larger than 1, you think of it a real number, then you're making it bigger. When you multiply it by a number smaller than 1, you're making it smaller. Okay, great. Now, that is what a complex vector space is. So basically what it says is that you can add, subtract, and scalar multiply these vectors. And very nice. You can't multiply the vectors yet. I mean, you can't multiply the vectors, so usually can't, but we'll talk about something much later on where you can, but we're not talking about that now. Okay, great. So now we need lots of examples of complex vector spaces. Okay, so let's do this. You ready? C, complex vector spaces, M cross N. Okay, what this is matrices, M by N matrices. Okay, and it's kind of, these are telling you what the objects are, and you're picking out complex numbers. Those are those are matrices, M by N matrices with complex number entries. Okay, let's just talk about the operations. Well, you can add two matrices of the same size. So that's that. You can put a minus in front of every element of the matrix and you get another M by N matrix. So that's another thing. The 0 is an M by N matrix with all zeros in it. Only zeros in it. So that's the same thing. And the main point is, take an M by N matrix, add the 0, you get A. So it works. Also, take an M by N matrix, take the same matrix, put a minus in front of every element. When you add them together, you're going to get the 0 matrix. So it works like that. Question: what's the scalar multiplication? So we did the plus, we did the 0, we did the subtraction. What's the 0? Take a matrix, take a complex number, okay, and take this complex number. So this is a M by N. This is M times N different numbers, complex numbers. Multiply every one of them by this C within the numbers. So let's do an example. Let's take this 5 times, we're going to do a simple example, 3.1702. Okay, so this is really a complex matrix, but I don't have any i's in there, and this could be a complex number. I don't have any i's. I don't want to start doing complex multiplication, but this becomes 5 times 0. This is the same size. 5 times 0 is 0. 5 times 2 is 10. 5 times 3.1 is 15.5. 5 times 7 is 35. So that's called scalar multiplication of a matrix. Very nice. Okay, great. This is a very general, obviously for every M and N, there's going to be a different complex vector space. Okay, next. C cross M cross, C to the M cross 1 power. This is really C to the M, And the idea is as follows. This is just complex numbers. This is a row of complex numbers. So this is C1, C2, C3, C4, Cm. Okay? And this is the main example that we're going to think of a lot of because it's going to be our most important example. Let's just say what it is. If you have one complex vector like this, and another one, we'll call it D1, D2, D3, D4, Dn, okay? Then you can add them as C1 plus D1, C2 plus D2, Cn plus Dn. No problem, okay? But there's a visualization of this. And the visualization is to think of these as real numbers, and you have a n-dimensional space and you have that, okay? If you have another vector, you have this. So we'll call this C, we'll call this D, and adding them basically corresponds to doing that, completing the square, the quadrihedral, the four-sided thing, and this is C plus D. Okay? When you add the numbers, that's exactly what you're doing. Okay? Let's talk about the scale. Oh, I'm sorry. What's this? So that's addition. What's subtraction? Just put a minus in front of every single number. Okay, great. What's the zero? Just have a bunch of zeros. Okay, that doesn't add anything or change anything. What's the scalar multiplication? If you do C times C1, C2, Cm, C is some complex numbers, here's M other complex numbers, you get C times C1, C times C2, C times Cm. Okay, and what that corresponds to is extending or shrinking the vector. Okay, great. So this is a special case of this where n is 1. Another way of saying that is an m vector, a vector with m elements, is really an m by 1 matrix. Okay? M rows, 1 column. Okay, so that takes care of that. Okay, a special case of this is C to the 1 cross 1, okay? And that's basically just complex numbers. Complex numbers by themselves is a very short, small, it's not the smallest, we'll see what the smallest is in a second. It's one of the smallest complex vector spaces. And basically the addition is, well, you can add 2 complex numbers. You can subtract 2 complex numbers. There's a 0 in complex numbers. And scalar multiplication is C times C prime. Just multiply the numbers. No problem. Okay. So this is a special case of this, which is a special case of this. If you want, you can think of a complex number as a 1 by 1 matrix with a complex number in it. Nothing shocking there. Okay, let me talk to you about the world's smallest example of a complex vector space, 0. It has just 0. It has only 1 vector in it, and it's the 0 vector. And basically, you add 0 to itself, because there's nothing else to add it to, and you get 0. You can multiply this by any complex number. Complex number times 0 is 0. You can subtract, you get 0. Nothing to it. So this is the world's smallest example of a complex vector space. Great, let me show you another one. Polynomials with complex coefficients. Okay, let me show you what that is. So, how about this? 5 plus 3i x to the 5th plus 6 minus 2i x to the 4th plus 3.2 plus 4.9i x squared, okay, plus 13x plus 6i. So this is a fifth dimension of, fifth exponent. This is a polynomial to the fifth with a fifth power in it. Each one of the coefficients are complex numbers. Well, this is a complex number. It happens to be a real number, but it's also a complex number. And this is a complex number. This is, if you want, this is x to the 0. This is x to the 1. Okay, fine. This is a typical polynomial. So a typical polynomial with complex coefficients is a vector. Okay, and let's go through the operations. Plus, just add the polynomials, which basically means you're adding the coefficients. Okay, minus just means put a minus in front of each of the coefficients. The 0 polynomial is the stupidest polynomial in the world. X to the 5th plus 0, x to the 4th plus 0, x to the squared. Well, x to the 3rd is definitely 0, plus 0, x squared, plus whatever. Just a bunch of zeros. Whatever you put into that polynomial for x, you get out 0. Okay, so that's the 0 polynomial. Scalar multiplication is multiply by c. Multiply each of the coefficients by a complex number. Easy as can be. Okay, there's a okay, we didn't describe this yet, but there's a smaller complex vector space. Okay, and it goes as follows. That was called polynomials with coefficients in C, but this is called polynomials with an n over there. And what this is polys with complex coefficients with nothing higher than x to the 5th, or x to the n. Okay, so this is all polynomials where the highest coefficient is n. Okay, so there's poly of 1, there's poly of 2, there's poly of 3. There's a lot of different of these, depends on what n is. Okay, and they're all sub-vector spaces. In other words, they're subsets that satisfy the same requirements as poly of C. This is all possible powers. This is only till power of n. Okay, great. Let's talk about another one. Ham of n to the c. So this is really ham of sets, actually. These are functions. I'm sorry, let me tell you what the vectors are. They're functions from the natural numbers to the complex numbers. Main point. Given two such functions, okay, you can add them. So f plus g also goes from the natural numbers to c. And how is this defined? F plus g of a natural number, so that's some guy in there, is equal to f of n plus g of n. Okay, so that's where you add two functions. You can actually add two functions. Great. How do you subtract two functions? Very simple. You ready? Minus. Can't get simpler than that. What's the 0 function? Very simple. 0 goes from the natural numbers to c. Okay, now I have to tell you how this is defined. 0 of n, that's an input here, is going to equal to 0. It always outputs 0, no matter what. It's a stupid function that always outputs 0. Great. Now I got to tell you what scalar multiplication is. So here's a nice function from here to here. Here's a nice function from the natural numbers to complex numbers. Want to say hello? No. Nope. Yeah. Here's a nice number. Here's a nice function from the natural numbers to the complex numbers. Take a number c, scalar multiply it. So this is a new function from the natural numbers to c. I want to see how this function is defined. So we do as follows: c times f of n, that's a typical input here, is going to equal to, you ready? C times, this is a complex number times f of n. F of n is a complex number. Here's a complex number times a complex number. No problem. And it satisfies all those requirements. Okay, great. Let me just point out two things here. One, I didn't really use the structure of the natural numbers. When I was adding them, let's just do that again. F plus g goes from the natural numbers to the complex numbers. Okay, when I was adding them, the addition took place in here. When I scalar multiplied them, the scalar multiplication took place in here. Didn't do anything with the natural numbers. Didn't do add natural numbers or subtract. So turns out I can use other sets here also. Let me just show you what's going to show up, what's going to arise the rest of this course. Okay, you can talk about functions from the complex numbers to the complex numbers. And so again, the vectors here will be a function like this. And you can, if you have two such functions, you can add them. You're adding them over here. Okay? And you have scalar multiplication, and you have subtraction, and you have a zero function. No matter what you input here, it's going to output the zero of this complex number. Okay? Let me give you one other. Take any set whatsoever. The homomorphisms from the set to C is a complex number. Okay, now in the book, there's a very, 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 very important, how many varies did I have? Very, 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 very important. 3 varies. Okay, hold on. Does everybody want to say hello to my daughter?
No.
No, she doesn't want to talk to you. Okay, there's a very, very, very important thing. It says as follows: if you have a category A, and you have two objects in the category, A and B, okay, then you can look at the homomorphisms from A to B, the functions from here to here, okay? Main point, and this shows up over and over. If this B has extra structure, then this set of functions, or class of functions, has this extra structure, inherits the structure. So how B inherits, in other words, it gets a lot of the same structure, the structure of B. Okay, let me show you what that means. The complex numbers is a complex vector space. We just saw that. Okay, take any set, it's also a set, by the way. Take any set, from S to C, inherits the structure of C, and this set also becomes a complex vector space. So this new set of functions from here to there is also inherits the structure of the complex vector space that this is. C itself is a complex vector space, so it inherits the same structure. That's something that we're going to see over and over. Okay, so let's say it again. The set of morphisms with codomain B usually inherits a lot of the structure of B. Depends what I mean by structure and things like that, but that's an important categorical point which we will come to many times in the coming pages. Okay, great. Next. Okay, so we now know what a complex vector space is. Guess what? We're going to talk now about a subvector space. Let's say where we saw this, we talked about subcategories. What's a subcategory? It has part of the structure,
but it's different.
But it's different. It's not the whole thing. Okay. This, by the way, could be the whole thing, but it's not. It's different. So, what's a subvector space? Well, it's a subset of these guys. This guy is a subset of these guys, but they share the same operations. So the plus and the scalar multiples, and the zero is in here also. The zero is not only in here, but it contains this. So if you want, here is a vector space, okay, and it has a zero vector in it, and V prime also has that vector space. So that's the way you write a subvector space. Okay, great. Okay, but main thing is, if you have two vectors in this subvector space and you add them, or you scale or multiply, then you're going to land in there also. So it's closed under, what you say is, it's closed under this. In other words, this by itself is a vector space. Okay, so the book goes through a formal definition, exactly what it means, but we have an intuition of what it means, and we can go on. Great. That's the end of the first part of the lecture. So I told you, it's this category consists of two things: complex vector spaces and morphisms between complex vector spaces. So the rest of this video is going to be about morphisms between two complex vector spaces. And it's very, very important. So, you ready? Given a vector space V and another vector space V prime, I can talk about a function from V to V prime. Okay?
Which is just a fine word.
It's just a fancy word, because remember, V is a collection of vectors. V prime is a collection of vectors. So you map, this function takes a vector here to a vector here. That's it. But we want T to preserve operations. The operations in here and the operations in here. So let's be very careful what this means. This means that if you have two vectors in here, two little v's here, v and little v prime, maybe I should do v1 and v2. So we'll do v1 and v2 so that we can, the v primes are in here. So we have little v and little v1 and little v2. Great. And we add them together. So
Equals 2 V's.
it doesn't equal 2 v's, but it equals something in here. Okay. And then we take the T of it. So again, V1 is in here, V2 is in here. You add them, you get something in here. You take T of that. Well, guess what I want it to equal? And we saw this before. We saw this before when we talked about algebraic structures. So I told you a complex vector space is just an algebraic structure. Okay, so what do we want? We want it to preserve the operations. So here's the plus operation. Just to keep careful, I'm going to write V over there. Okay, that's capital V. So let's make that capital V. Okay, great. So that's the plus operation over here, and I want it to equal to T of V1 plus T of V2. Okay, now this plus takes place in here. Okay, and the idea is as follows. If I add two things here and I bring it over, that's the same thing as taking the image of what this is in here with one of them, then take the other one and then add them in here. So this operation is here, this operation is here, but you take this operation, you get that. Okay, I want to show this as commutative diagram because we love commutative diagrams. Let's do it. You ready? V cross V, V prime cross V prime. This is T cross T. We saw this before. This is the addition operation in V. That goes to V. This goes to T. This goes to V prime. We want this to commute. This is a plus, the V prime plus. We want this to commute. We saw this before when we talked about monoid homomorphisms, or algebra homomorphisms, or group homomorphisms. We saw this before. Okay, that's one requirement that we have. Okay, so one operation that we have is that they should respect the plus. Guess what the other one is? Well, let's do it. You have V1, that's an element in here. You could take a complex number and scalar multiply it. Very nice. Okay, I can take T of that. Okay, well, another thing I could do is take V1, take T of that, and do the scalar multiplication in here, C. Now, I'm just going to make this dot a little bit different. Its dot is the scalar multiplication in here. Here's the scalar multiplication in here. So we're going to put I'm going to put the v prime over here, and I'm going to put this as a v over there. So we want this to preserve, okay? Now, what about protecting, respecting the minus? Well, if you follow these two axioms, it's going to respect the minus 2. And another thing that's also going to happen is this vector space has a 0 in it, this vector space has a 0 in it. And without saying anything, t of 0 is equal to 0 prime. So this, if these two axioms are satisfied, automatically the 0 in here will go to the 0 in here. Okay, great. Okay, guess what? We got to talk about examples. Oh, I'm sorry. When you have such a map which satisfies such equations, it's called a linear transformation. I sometimes might say a linear map, but it doesn't matter. Okay, so very nice. Okay, now we need lots of examples of this. We love examples. Okay, so let me just give you 2 quick examples. Let's say V1 is a subvector space of V prime is a subvector space of V. So there's an inclusion map. There's a way of including little V prime includes into here. So if you want, you can think of this picture as this. This goes into this, which goes into here. So this is V prime, this is V prime, this is V. One includes into the other. Well, the map that brings everything from here into there is also a linear transformation. It satisfies both of those requirements. That's one example. There's another thing called, so this is the inclusion map, the inclusion linear transformation. Transform one vector space into another vector space. Okay. Okay, great. Next. Okay. There's another map. Given any vector V, and any complex vector space V, and any complex vector space W, there's a map called the null map. Okay, or the null natural transformation. I'm just going to call it T, but I'm going to say it's the null map, and it's defined as follows: T of little v is equal to 0. Is 0. Tell them I'm doing this. They should be quiet. Okay, so we have that. T of v is equal to 0. Okay, let me just draw a picture of this. This is V. This is W. Here's the 0 of this vector space. And this goes like this. Every single thing just goes to the 0. It's a very stupid map. It just takes everything to 0. But, main point, it satisfies the requirement. Okay. Okay, we need another example. Can you tell them? Okay, we need another example. More examples of linear transformations. Okay. Let A be, so let A be an m by n matrix. Okay. We're going to use this matrix to make a transformation. Okay, and so we're going to make a transformation T. It's going to be based on A. Okay, and it's going to go from, got to make sure I get this right. Right. C to the n rows of n complex numbers. columns, vectors of n complex numbers to vectors of m complex numbers. Now let me tell you how it's described. Take a typical vector in here, okay, and T of A of it is going to equal to A, that's an M by N matrix, okay, times V, which is an N by 1 matrix. They match up, so you get out afterwards this whole thing. After you multiply it, it's going to be an M by 1 matrix. And that's exactly what you get here. Okay, so you input an N vector and you output an M vector. Okay, we have to show that this is a nice linear transformation. How do we show that it's a nice linear transformation? So we have as follows: T of A of V plus V prime. We have to show it respects the addition. So this is going to equal to A times V plus V prime. Okay, and in fact, this is matrix multiplication. Matrix multiplication distributes over addition. This is vector addition, and so this is equal to AV plus AV prime. Okay, and this is another way of saying T of A of V, and this is another way of saying T of A of V prime. So this is equal to this. So it preserves addition. It also preserves scalar multiplication, but we don't have to write that. We don't have to deal with that. I mean, whatever, we can show that, but it's not necessary right now. Okay, great. So such matrix-induced linear transformations are going to show up a lot. In fact, a lot. Okay, great. Let me show you another example of a linear transformation. Okay. So there's a linear transformation T, which goes from C to the M cross N to C to the N cross M. So this is M by N matrices, this is N by M matrices, okay? And basically T of A takes such a matrix, an M by N matrix, and just do A transpose. That means flip the matrix in half, flip the matrix. Transpose operation is a well-known operation about matrices. The ij position is equal to A of I comma j comma I. So you flip it. Anyways, A is an M by N matrix. A transpose flipped is an N by M matrix. Okay, this also has to preserve the addition. What's the addition? The addition of matrices. So what do we need? T of A plus A prime equals A plus A prime transpose, okay? And the transpose goes inside. So this is equal to A transpose plus A prime transpose, okay? Which is equal to T of A plus T of A prime. So it works. T respects the addition, okay? And the same thing for scalar multiplication. Okay, we can do that. C dot A, take a matrix, take a complex number, multiply every entry of that, T of that. So take the transpose of that. That's the same thing as T of A. Take the transpose of the matrix and multiply every entry by C. So again, we're not doing anything. We're just changing the position of the elements. That's what the transpose operation does. Okay, great. So those are lots of nice examples of linear transformations. Okay. What's our next step? Okay, so we have these linear transformations. We have these morphisms in the category of vector spaces. What do we want to show? What do we want to show that it in fact forms a category? And the answer is if you have a vector space, and you have another vector space, and you have another vector space, and you have a linear transformation here, and you have a linear transformation here, then guess what? They compose. Okay? Okay? And, so what should we call this? T compose T prime. Okay? But we have to show that this composition respects the addition. Okay, and the way we do it is we show that, well, this composition is made up of this map and this map. This respects the addition. This respects the addition. Therefore, the whole thing will respect the addition. It pays to go through the details at least once in your life. So let's do it. T prime compose T of V plus V. I want to do, that's little v. Let's do V1, V2. Okay, those are two guys in here. Okay, well, what's this equal to? Well, it's equal to T prime composed T composed V1 plus V2. Okay, good. That's the definition of composition. This composed with this is that. Okay, great. Now, what do we know about T? T is assumed to be a linear transformation, so it's going to respect that. So what do we get? We get T prime, we're working from the inside of the parentheses first. T prime of T of V1, okay, plus T of V2. Close that off. Hope you're in the screen. Hold on, let me check. Yeah, you're in the screen. Okay, good. Next, let's go through this. This plus takes place in V. This plus takes place in V. This plus takes place in V prime. Okay, so maybe we'll put a prime over there. Okay, great. What do we know about T prime? Well, it respects the addition here and brings it into the addition here. So this is going to equal to T prime, and it's going to do two parts, T of V1 plus T, this T prime respects that, T prime of T of V2. Okay, and this is exactly T prime compose T of V1. I'm sorry, this addition is now in here. Okay. Plus T prime compose T of V2. Okay, that's exactly what we mean to show. You also have to show it's true for scalar multiplication. It's even easier. It's done in the book, but it's something that you have to see. Okay, great. Okay, great. What else? Well, guess what? If we had a fourth vector space, and we'll call this map T double prime, then we can compose like this, and we can compose like this, and then we can compose like this. Main point, linear transformations composition is associative. We've seen this a lot. Okay, and the idea is as follows. It's not something very strange. The main point is that T prime, T triple prime, T prime, T double prime are functions. They're functions. They carry elements to elements. The only thing is these functions respect the operations, but they are functions. And whenever you have functions that carry set elements to set elements to set elements, it's associative. So there's nothing to worry about. Furthermore, for any vector space, there's a special morphism called, there's a special linear transformation called identity of V. Okay? And composition respects this identity. In other words, you have that unit rule. So let's just do it. T composed identity of V is equal to T, which is equal to identity of V prime, which is equal to T composed identity. And one of these is on V prime and one of these has this. So let's do this. This is T, and then this is V prime, and this is identity on V, and then T. Okay? So it satisfies these rules. And finally, we can make a nice definition. You ready? So the linear transformations are associative and they satisfy the unit rule. Conclusion, there is a category called CVect. The objects are complex vector spaces. The morphisms are linear transformations, and it's a totally legitimate category. Let's talk a little bit about some of the properties about it. It is for sure locally small. I'm sorry, it's a large there's a class of vector spaces, I suspect. Yeah, there's a class of vector spaces, of complex vector spaces, but the homomorphisms it's locally small, and we're going to see that in a minute. Okay. Does it have an initial object? No, I don't think it has an initial object. I think it does have a terminal object. Okay, there is a terminal object, namely that world's smallest vector space. Okay, for any complex vector space, there's a unique morphism like that. We called it the null map. So there is a terminal object. There is no initial object. Is there an initial object? I'm sorry, maybe 0 is an initial object. Yeah, 0 can only go to 0. So yes, there's an initial object. So 0 is not only is 0 the terminal object, it's the initial object, and it is the and just so it's a 0. It's an initial and terminal object, so it's a 0 object. Okay. Anything else? Oh yeah, we have to talk about monomorphisms and epimorphisms. Let's do that right now. I'm sorry, we'll do that in a few minutes. We have to make another definition. Okay, ready? I just want to make an analogy or something. I want to show an interesting thing. Let's talk about set. In set, a one object set maps like that picks out a element of the set. Okay, great. Now, let's talk about in complex vector spaces. Let's see what happens. If I take the 0 element, or the 0 vector space, okay, and I look at that, what's it going to do? Well, it's just going to choose, the 0, because 0 goes to 0. Okay, it's part of the definition of, it's a consequence of the definition of a linear transformation that 0 goes to 0. So that's not a very interesting thing. It's unique, it's not very interesting. If S has more than one element, there's not going to be a unique one like this, but this is unique, so that's not very interesting. Okay, let me show you what is more interesting. That's a complex vector space. That's a vector space. There are a lot of different morphisms like this. Okay, okay. Now, but if you think about it, there's an element here 1. That is a complex number, okay? And this 1 will go to T of 1, okay? Now, take any other number, complex number. You can think of that, take a number C, you can think of that as T times 1. Okay? C times 1 is C, so we can think of it like that. Well, by t of C times 1 is going to equal to C times t of 1. The point is that this map is totally determined by where 1 goes, because any scalar multiple of 1, well, any other number is a scalar multiple of it, and so it goes like that. So this map from the complex numbers to any complex vector space is totally determined by 1. Okay? But in fact, it's not like this, that one element picks out one element here. Yes, the complex numbers, the 1 goes to some element, can go to any element, but this map doesn't pick out one element, it picks out a whole array of elements. Okay? So the idea is as follows. For every one, basically, the output of this is t of 1, okay, and all complex multiples of t of 1, okay, all complex multiples of t of 1, all scalar multiples of t of 1. So it picks out a whole array of vectors. It picks out a whole array of vectors where the array is described by this complex numbers. Okay, so this is something, and we're going to see later on, it's kind of important in the quantum world. But it's a very interesting thing to make this analogy between a one-element set picks out an element here, a map from this simple complex vector space, so this is a simple set, picks out a thing, a map from this simple complex vector space is going to pick out an element, but it's also going to have a list of all the elements are going to come out there. So it turns out that there's a lot of such maps. Okay, that's going to be important. Okay, great. Next. Okay, great. Let's take a vector space V and a complex vector space V and a complex vector space W, and let's talk about a linear transformation. Now, what happens is as follows. There's going to be two subsets. For every linear transformation from V to W, there's going to be two important subsets. And I'd like to draw a picture for them, of them. Okay, so this is V, and this is W, and T goes from here to here. Okay, so we have that. So here's T. Okay, so one subset is like this. There's a particular element here called 0. Well, why don't we look at the subset of these elements of V that goes to 0. Okay, so that thing, this core, this part, by the way, 0 goes to 0. We saw that before. But a lot of other elements might also go to 0. Okay? And so let's call this a name. So this whole thing is V, but there's going to be a subset of V called the kernel of T. It's the part. It's like the main part that goes to that, the kernel of a seed or something like that. Okay, let's formally write it. So we're going to write it as follows. The kernel of T is equal to those V member of V such that T of V equals 0. That takes care of that. Okay, so that's a subset of this. But turns out it's more than just a subset. Ready? It's a subvector space. Okay, which means if you add two elements that go to 0, then the addition of them also goes to 0. Okay, so that's very nice. Okay, now we want to talk about another subset, and we're going to spend the rest of this class talking about these two subsets. Okay, there's a subset around here also. It's called image of T, and what is it? It's all the possible outputs of this of this map. So it's all the possible outputs of the map. Okay, so let's write it like that. Okay, so it goes as follows. The image of T, IM for image, in other words, it just looks like the image. You know, what this is a transformation, so tell me, what does it transform to? It doesn't necessarily hit these guys. It might hit the whole, all of them. By the way, if it hits all of them, by the way, in set theory, this is called the range, but fine, here we're calling it the image. If it hits all of them, then it's a surjective map, but we're not doing that. Let's just, we'll get there in a minute, okay? So what is this? This is equal to little w's in W, such that there exists, okay, that's what there exists a V member of V and T of V equals W. Okay, so every guy in here means what? That there's some guy in here that hits it. So this is little w, and this is little v. Okay, so again, let's just restate it. For every linear transformation, there's a subset here, and there's a subset here. Main theorem, this subset is a subvector space of V. This subset is a subvector space of W, and it's very nice. Okay, now we have to show that it's a subvector space. Basically, we take two elements here, we add them, we show that they're still in there. We take a vector in here, we multiply it by a complex number, scalar multiple, we make sure it's in there. Same thing here. We take two things in the image, make sure that when we add them, we still get something in the image. Take two vectors in, take a vector in the image and a complex number, make sure that when we multiply it, we get something in the image. Okay, now, question, what does this have to do? Well, I'm sorry, we're going to see a lot of different places where this is used, but let me just make a statement. Theorem, T goes from V to W. The following are equivalent. T is monic. Okay, so we had this last class called monic means left cancelable or right cancelable or something like that. Okay, the same thing is T is injective. I'm sorry, I might have used one-to-one. Okay, these two are equivalent, but there's another way of saying this also, namely the kernel of T is equal to the world's smallest complex vector space, 0. Okay. Okay. Main idea, if the kernel, if only 0 goes to 0, nothing else, then this is actually a monic. It's an injective. The whole function is 1-to-1. Okay, let's do another one. T is epi, or epic, or epimorphism, if and only if T is onto, we used another name for onto, surjective. Okay, so that relates this notion of injectivity, whatever, with these things. Notice the word image is not used in this, and I'll show you why in a second. Okay, great. So this relates these categorical notions of monic to things that are actually in the category. Very nice. Okay, now I want to talk about basis and dimension. Okay, so we want to talk about A basis is kind of like a core of a vector space. Again, when we saw the core of a linear transformation is kind of the kernel, but it's kind of the core of the vector space in the following sense. Okay, so we have to talk about a linear combination. Okay, and the idea is as follows. Let's say you have a bunch of vectors, v1, v2, v3, v4, dot, dot, dot. I'm not saying this is a finite set. And you could scalar multiply these with C1. That's one complex number. Here's another complex number. Here's another complex number. Here's another complex number, dot, dot, dot. You can scalar multiply these little vectors times this. And one of the things we saw is that you can add them. By the way, take V1, multiply it by a complex vector, by a complex number, you're still in V1. So you're talking about, you're in a complex vector space V, you pick out these vectors, okay? They're still there, okay? Scalar multiply, they're still there. And you can also add them, okay? So complex vectors are closed under scalar multiplication and addition. So it turns out that this thing, and you might go on forever, is equal to some vector here. So we'll call this vector y. Okay, and the way we say this is that y is a linear combination. Linear because we added it and we scalar multiplied. Y is a linear combination of these vectors. v1, v2, v3. Very nice. Okay. Okay, so again, given any v's, given complex numbers, you can get that. Okay, great. Now I want to talk about what's something called a basis. You usually write it with a script b, okay? And these are special types of vectors. Instead of calling them v, I'm going to call them b1, comma, b2, comma, b3, comma, dot, dot, dot. I'm not saying it's finite. I'm not even saying it's countable, but it doesn't matter. I don't want to get into that. Okay? And the idea is as follows. B is so these are vectors in this vector space. And I want to say that they are the core of the vector space in the following sense, is that every vector in V can be written as a linear combination of these guys. So again, there's a concept of linear combination. You can do it with any vectors. But if you have the fact that any vector, I left out one important thing, can be written as a linear combination, what does that mean? That for any y member of V, y is equal to b1, b2, b3, dot, 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 okay? And furthermore, it can be written as a linear combination uniquely. What do I mean by that? That there's a unique C1 and a unique C2 and a unique C3 such that we can add them and y can be described by it. So what you have is, here's your vector space V. There are special vectors, we'll call that B, and any vector in V can be written uniquely as a linear combination of these guys. That's called a basis. Okay? Now, I just want to say, for the most part, we're going to be dealing with a finite basis. Some vector spaces have a finite basis. There's a finite way of doing it. Some vectors, you need an infinite ones. We'll see examples of both. Okay. In this case, where there's a finite number of vectors that describe every single vector that describe with a linear combination, uniquely describe every single vector in here, we say that okay, fine, stop, sorry. Okay, so every single vector can be there. Great. Question. What happens if you have another basis? You can have more than one basis. Okay? Okay, there could be more than one basis. So another set of vectors, okay, might also describe that. That's very nice. Could happen, it happens all the time. Okay, main point is as follows. Two bases of a vector space, complex vector space, it's true for any vector space, has the same number of elements. Okay, I'm going to give you an example, two examples. This flat space can be thought as a 2 as a vector space. Basically, any single point here, there's an arrow to it. Okay, if you want, you can think of this as 0. This is a flat space, and I can describe all the points on this thing by these two arrows. A little arrow here and a little arrow here. Okay, and basically any arrow, like from here to here, can be written as a linear combination of these guys and these guys. So these two arrows describe every single dot on this whiteboard. Okay, that's one example. Next, 3 dimensions. I live in 3 dimensions, although you're only looking at me in 2 dimensions. I live in 3 dimensions, and every single dot here can be written as, here's a nice little basis here. One arrow going this way, one arrow going this way, one arrow going the width. So width, length, height, depth, those are 3 dimensions that describe everything. Okay? Okay? 2 bases of a complex vector space has the same number of elements. My examples are about real vector spaces, but it doesn't matter. Has the same number of elements. So B, the number of elements in B, is equal to the number of elements in B prime. Okay? They could also be countably infinite or uncountably infinite. We don't care. If they're finite, we say they have dimension n. If they have n, we have to say, well, you can say their dimension is the number of elements in the basis. Okay, so this whiteboard is a 2-dimensional space. This room is a 3-dimensional space. Okay, and because the number of vectors here is the same as the number of vectors here, so I can say the dimension of any basis, the number of elements in any basis is the dimension. Okay, so it's a well-defined notion. We need some examples of these bases, and we need to see what their dimensions are. Okay, so let's go through our examples of vector spaces and see what type of bases they have. We're going to deal with very simple bases. But later on, there are always more complicated bases. Okay, great. So you ready? Okay, so the first vector space that we dealt with was M by N matrices. Okay, and let me show you what that basis looks like. Okay, here's 1 with a bunch of zeros. All the other entries in this vector space is, in this matrix is 0. Here's one of the elements of the basis. Here's another one, 0, 1. Everything else, 0, 0, 0. Okay, here's a third element of this basis. Okay, so basically, every entry of the matrices has a 1. Okay? And it turns out that any matrix can be written as, well, let's say you have the word 15 here, so it's going to be 15 times this. You have the 2 plus 1i, 1.1i, well, it's going to be 2 plus 1.1i. That'll be scalar multiple times that. Scalar multiple times that. You're going to have a minus 6 over here, so we're going to scalar multiply this by minus 6. Then add them all together, and you get the whole vector, the whole complex number, the whole complex matrix. So again, every matrix can be written as a linear combination of this matrix plus this matrix plus this matrix, dot, 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 all the way down till the matrix that only has a 1 over here, all the rest are 0. Okay. Okay, great. What's the dimension of this space? Answer, how many elements, how many basis elements do I have? And the answer is m times n. I have m rows, n columns. I have m times n entries. Great. Okay, let's look at another example of a complex vector space. How about this? M cross 1. So this is complex vectors of size m, okay, with m entries, and basically it's the same trick. 1, 0, 0, 0, 0, 0. Here's one element of the basis. Here's another element of the basis. Sorry, I should have skipping here. And here's a third element of the basis. And this goes on till here you're going to have 0, 1, dot, 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 I'm sorry, 0, dot, 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 0, zeros all the way here. And the last one is 0, 0, 0, dot, 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 0 with a 1 over there. So matrices with exactly 1, 1 in them, that forms that. How many such matrices are there? M. So the dimension here is m. Can't get simpler than that. Okay, great. Okay, let's look at our third example of complex vector space, namely 1, the complex numbers. Okay, well, this is totally generated by this. Let's restate this. Every complex number can be written as a linear combination of this guy, c times that. And like I just said 2 minutes ago, c is equal to c times that. That's it, finish. So this complex vector space has dimension 1. Okay, great. Let's look at poly of n. Okay, what's poly of n? So I need to find polynomials such that any polynomial, I need to find a list of polynomials such that any polynomial in here can be written as a linear sum of that. And the answer is very simple. 1, that's a nice polynomial just by itself. Here's another polynomial. Here's another polynomial. Here's another polynomial. Here's another polynomial. And basically what this says is that any polynomial of size at most n can be written as some complex, let's write that as C0, some complex number like that, times a complex number like that, that has a secret 1 over there, times a complex number like that, times a complex number like that, times a complex number like that, okay, with lots of pluses in between. Okay? So, conclusion, let's just restate it. Every polynomial in here can be written as a linear combination of these guys. Conclusion, the dimension of this is from 1 to n, but don't forget this. So the dimension for this vector space is n plus 1. Very nice. Okay, next. I can do this a little bit easier. How about unbounded complex numbers? I'm sorry, complex vector polynomials. And the answer is just keep on doing this forever and ever. X to the n plus 1, x to the n plus 2, dot, dot, dot. Conclusion for this, the dimension is countably infinite. Countably infinite. Okay, great. Okay, I want to do something a little bit weirder. Again, we're just doing every single example of complex vector spaces that we talked about. We want to talk about how many things they have. So let's just do this one. Hom of n comma c. Okay, natural numbers to the complex numbers. I think I also call this in the book functions from the natural numbers to the complex numbers. And as we said, they inherit the complex vector space structure of C. Okay, so I want to know what the bases of these are, and the answer is there's a function called f of I. It's a funny function. Okay, it goes from the natural numbers to the complex numbers. So it's one of these guys. Let me tell you how it's defined. F of I, you give me a number n, it's going to either output one of two things, 0 or 1. By the way, 0 is a complex number, 1 is a complex number, so this is not a problem. Okay, so when does it output 1? When n equals I. Otherwise, it outputs a 0. Else. Okay, so this is a special function. It always outputs 0 except once when it's the number I. Okay, great. Now, I want to show you that any function like this can be written, any function can be written as a sum of these guys. Okay, so let me just write the formula for this. Okay, it's a cute little formula, and it goes as follows. F is equal to, we write the sum as follows, I equals 0 to infinity of f of I, sorry, let's write this. Okay, so this is these special functions that only output ones, one place, okay, and we're going to multiply that f of I times that. So this function, any function from f from n to c, okay, can be written as a multiple of, you add them all together of f of I, so these are these special functions, and you plug out, this is going to be a complex number, this is a complex number. So this complex number times this. Main point is, how many of these f of i's are there? Countably infinite. Okay, so this is a countably infinite complex vector space. Okay, great. Now we could talk also about. Let's erase this for a second. Actually, let me just say it. We could talk about complex numbers from here to here. This is uncountably infinite. The basis has uncountably number of elements. Okay, and given any set S, this forms a complex vector space, okay? And the dimension is equal to the number of elements in S. Can't get simpler than that. Okay, I want to talk about a main theorem. Lots of things fall out of this theorem. We're not going to really talk about a lot of the consequences of this theorem, but it's a fundamental theorem, and it's called the fundamental theorem of linear algebra. Some people call it that, so I don't want to write that whole thing out. The fundamental theorem of linear algebra. It's also called the rank nullity theorem. And it says as follows. Ready? Let's put up the picture that we had over here before. You have V, you have W, you have 0 of W, you have 0 of V. Okay? And we have a kernel over here. That's all those elements that go to 0. We have, so let's write that. Kernel T goes from V to W. So this is the kernel of T. Very nice. And we have the image of T. And that's basically where all the outputs go. And now, we saw this is a subvector space, this is a subvector space, but we want to relate all these things in terms of dimension. And that's why this theorem is so fundamental. So we have this notion of dimension, so I want to know what these things are. So here's the way it goes. Ready? The dimension of the kernel of T. So that's how small this is, or how big this is, or this is how, by the way, we're not proving this here, but I prove it in the book, and we talk about how many elements are in the basis over here, okay, plus the dimension of the image of T, okay, so how many elements are over here, how many elements are in the basis of this, okay, is equal to the dimension of V, this guy. In other words, you can figure out how many ways are there in describing this by seeing how many things get crunched to 0 plus how many things are in the image, and then you get the whole thing. Not a simple theorem to prove. It's done in the book on page 78 and 79. It's done in the book on page 78 and 79, but it shows up very often. Question. Sorry. So that's a beautiful theorem. It's an important theorem. It's a beautiful theorem. Basically says, besides for crunching this plus this, you get this. And basically the way it's proved is as follows. You find a basis that's over here, and you relate this basis to this basis and this basis. Okay? Okay. Question. What about the dimension of W? And the answer is, W doesn't play a role here, and let me show you why. Because I could do this for here, but also I could have a bigger W. We'll call it bigger W prime. Or I could have even bigger W. W double prime. Okay? That's not... Once you have a vector space, you always have a larger vector. You can think of a larger vector space to do it. That's not the point. The point is, how does this V fit in here? How many things were crunched down to being the 0? How many things were crunched down to go to 0? And how many things were in the image here? Okay? Okay, let's just take a special case of this. We said as follows. What happens if the kernel is just 0? That's the world's smallest kernel. This shrinks to 1 point. Okay, that has 0 dimension. Okay, so then we're not dealing with this. We're just dealing with that. Okay, and there wouldn't be the kernel would be trivial. The kernel would be very small, so that would just be here. And this is the kernel, it's one thing. So then this would go to 0, and the dimension of the image of T would be the dimension of V. In other words, this doesn't crunch to anything, and so this is 0, so the dimension of the image of T is equal to the dimension of V. Okay, this is very, very different than sets. Sets, you can have all types of mean and nasty things happen, but in complex vector spaces, everything is so controlled that this would never have, that you can make such a beautiful theorem like this, relating the image to where you're coming from, the domain to the codomain. Okay, a few more small things about complex vector spaces, namely, if V is isomorphic, that's where we write isomorphic to W. I'm sorry, I shouldn't have said if. V is isomorphic to W if and only if the dimension, oops, I've been using lowercase the whole time, so why change? The dimension of V is equal to the dimension of W. Now, what this means is as follows. Essentially, there is only one complex vector space of dimension 5. There is only one complex vector space of dimension 32, essentially. So, if you have two complex vector spaces and they have the same dimension, then they're isomorphic. They're kind of the same, just up to renaming. Okay, so if you want to think of it that way, then I'll give you, here's the complex vector space of dimension 5. You ready? That's the simplest one to talk about. Here's the complex vector space of dimension 32. Vectors of size 5, vectors of size 32. Okay, so that sums up a lot of things. That makes complex vector spaces very easy to study because you're basically studying these vectors. And that's exactly what we do. Okay, except for when you get to infinite dimensional. But again, there's only one complex vector space of countably infinite. There's only one. So that's a little bit easier. Okay, that's very helpful. I'm sorry, I didn't prove that theorem, but I don't think I even prove it in the book. No, I do prove it in the book. Yes, I do prove it in the book. Okay, great. Let's close off just talking about 3 different operations on vector spaces. So this is something we always do. We always talk about this. We introduce a notion. We talk about morphisms between the notions. So we introduce complex vector spaces. We talk about linear transformations between them. But we also want to talk about operations on complex vector spaces, which means things you can do to complex vector spaces to get more of them. So let's do the following. You have V1, that's a complex vector space, and you have V2, that's another complex vector space. And both of them are sub-complex vector spaces of W. So if you want, here's giant W, here's V1, here's V2. By the way, they all share a 0. Okay, they're both subspaces. Well, with this, you can form a new vector space called V1 plus V2. What are the vectors in this? So it's equal to that's little v, 1 plus little v2, such that V1 is a member of V capital V1. V2 is a member of capital V2. And that's it. So you add the vectors. So it's basically adding the vectors. So it's kind of like filling up this whole thing. It's going to have more things than just V1 and V2 because you can add them together. So it gets that. Okay, so this is called the addition of 2 linear vector spaces. Okay, there's more to say about this. Next, let's say you have Y is a subvector space of V. Okay, well, I'm going to be very sketchy here, and the book does it carefully, but I'm going to be very sketchy here. We can make a new vector space called V quotient Y. Okay, and we talked about quotient sets when we talked about equivalence relations. Let's remember when we talked about equivalence relations. So you have a set S, and you have a nice equivalence relation, and you want to talk when S1 is related to S2. Okay. So too, you have a vector space, and you have a subvector space, and basically, one vector V, we'll say V1, is related to V2 if V1 minus V2 is a member of Y. Okay? If this is true, okay, then you have a new vector space, and it's called a quotient vector space, and it works very nice. Okay, I'm sorry. In the book I talk about what's the dimension of this. In the book I talk about what's the dimension of this. I think it's V minus the dimension of V minus the dimension of Y. Okay, let me show you one other operation. So again, you could take two subvector spaces and make a third one, bigger one. You could take a vector space and a subspace and a subvector space and get a quotient space of that. Sorry, these two are not really going to be used that much. In our book, it's not going to be used that much. There's two examples, I think, in the book. Okay, and here's another thing you can do. Let's just remember about sets. I told you when we were doing the video about sets, we will always be coming back to the video about sets to get our intuition straight. So let's remember what we did in sets. So in set, okay, we had a set S, we had a set T, then we can look at, guess what? The function set from S to T. These are all maps from S to T. Great. In complex vector space, okay, we have a vector space V, we have a vector space W. Well, guess what? We can look at all linear transformations from here to here. And this is called, we're going to look at all linear transformations from V to W. This is called a function space. Okay, well, let's see. In set, this becomes a set. Given a set S and given a set T, we can form the operation and look at all the functions from here to here, and we get a set. Okay, great. Now, in vector space, we can look at this vector space, we can look at this vector space, we can look at all linear transformations from here to here. Guess what? It's not only a linear transformation, I'm sorry, it's not only a set, you look at the set of all linear transformations from here to here, but, you ready? It's also a vector space. Okay, what does that mean? Given T from V to W, given T prime from V to W, we can get T plus T prime, which goes from V to W. Okay, and it's done exactly the way you think it's done. Okay, it's done exactly the way you think of it's done. Let's just do it. T plus T prime of little v is equal to T of little v plus T prime of little v. Okay, so you can add them, and you can scale and multiply them, and it satisfies all the requirements. Okay, and there's a few more things. Okay, so great. So this was a tour, a giant tour in, I don't know, an hour and a half of basic linear algebra, dealing with complex vector spaces. There's a ton more, and there's a ton of applications for this, for all of this. And we're going to have another class, we're going to have another mini course called Advanced Linear Algebra. So we're going to see this again, this stuff again, with much more categorical structure. Okay, but let's go through it. Let's just go through it. We formulated the category of complex vector spaces. The objects are complex vector spaces. The morphisms are linear transformations. Complex vector spaces are a algebraic structure where not only can you add things, but you can also scale and multiply things, and they all satisfy requirements. Linear transformations are basically functions. They're functions of the underlying set, but they also satisfy, they preserve those operations that we had. Okay, and besides that, we talked about bases, dimensions, operations on vector spaces, and I can't stress how much applications this is. This linear algebra, machine learning is all about linear algebra. Much of physics is done with linear algebra. In mathematics, they show up all over. We're going to see a lot of it all over. Anyways, I strongly urge you to pick up a book on linear algebra and learn as much as you can of it. Okay, thank you very much. Have a wonderful day. Foreshadowing. So this is the end of chapter 2. Now we start chapter 3. Let me tell you what chapter 3 is all about. What we do is we look at inside a category, one category, and we look at lots of different structures that you can formulate within a category. So we did a little of this when we talked about basic properties. We talked about monomorphisms and epimorphisms and initial objects and terminal objects. We're going to do much more of that in a more complicated way. And then we get the notion of a product of two elements and lots of things like that. Okay, looking forward to seeing you.